Okay, so we'll be looking at one-shot hyperspectral imaging using phase reflectors. This work was done by Takatani et al. It was featured in CVPR 2017. Uh, so it was an interesting read for sure. So I'll start with the introduction and some background, highlighting the key contributions, go into the problem formulation, and then cover the implementation, experiments, results, and end with discussion and conclusion. So, as we know, hyperspectral imaging has many useful applications, material recognition, for example. The problem, however, is that hyperspectral cameras, at least the conventional way of capturing hyperspectral imaging, is really expensive and not accessible to many people due to the expense and the way that you capture the image. And also, it's very time consuming to capture a whole image since they capture a part of the wavelength at a time. Not all, but some. But all approaches are very time consuming to capture a whole image. So what this paper proposes in their one-shot approach is to use reflectors with filters, colored filters attached to them. So the idea here is that a light source will shine on the target, which will reflect in many directions. Um, you can see here the direction that's perpendicular, obviously, to the target will go directly to the camera. But all other directions will bounce off these reflectors a number of times before they're captured by the camera. And since the color reflectors are attached to, or colored filters are attached to these reflectors, the idea is that the spectrum observed by the camera is broader than it would have if it was capturing the target directly. Um, so some background in this area, as we already looked at, conventional methods, they are very expensive, difficult to access, and take a while to capture the image. So going into more detail here, like I was saying before, there's narrowband filters, tunable narrowband filters, and diffractive media. So if we take narrowband filters, they sort of capture a part of the wavelength and then have to do that multiple times until they've captured the whole wavelength. So this takes a lot of time to capture the whole media or the whole image. So there's also some approaches that have been done in computational photography. These do work well. They are accurate at capturing the image. However, they still are expensive and use equipment that is not readily accessible to everyone. There has been some work in one-shot hyperspectral imaging. However, all of them lack in different ways. Either their results or their approach can't be generalized, or they still use specialized or expensive equipment. For example, there's some work done where they were trying to estimate the spectral reflectance based on a given RGB image, based on assumptions of, the reflectance is normally distributed, and then there's some smoothness to the the reflectance. But this simply won't work because the dimensions of reflectance are higher than RGB. There's some work for using lookup tables and interpolating the reflectance, which worked to a degree but required expensive equipment. There was some work to model a mapping between RGB values and a spectra, but this will depend on the data that they used. So their model won't necessarily perform well in all cases. And there's been some work which uses kaleidoscope geometry. Um, It's been useful for measuring the bidirectional texture reflectance in scenes. It was used to make 3D for 3D imaging. There was one paper that used coupled mirrors to reconstruct an object based on the silhouettes of the object. And there's one other work that seems similar to the paper here, where they proposed a kaleidoscope add-on to a camera, which enhanced the capabilities of dynamic range, multispectral polarization, and light field imaging. So they mapped an input image to a 3x3 grid and then used 9 color filters to give it enhance the capabilities. The approach here differs from their approach in that um, here they only use a single color filter placed on the reflectors as opposed to 9. So some of the key contributions of this paper is their one-shot approach achieves reconstruction error on average of 14%. So we'll see in some of the images that they show, it's not perfect, but considering the accessibility and the cost reduction of their approach, it establishes some feasibility and it's definitely good results. The second is they've achieved couple magnitudes of cost reduction. So they state that their whole setup with mirrors and filters was less than $100 versus 10,000 or more for hyperspectral cameras. So going into the problem formulation, we start with um, a equation to model the intensity um, at a given for a given channel by the camera. So this assumes they state isotropic spectral reflectance on the surface under uniform illumination. So this is just to help the case where you don't have to worry about the angle of incidence or uneven lighting affecting our estimations. Um, and so they say that the observed intensity for the K channel is the integral for the whole wavelength being observed for L lambda, S lambda, and C sub K lambda. L lambda is the spectrum of illumination. S lambda is the spectral reflectance, and C sub K is the spectral sensitivity of the Cape channel in the camera. And so, as we saw in the model, when the light hits the target and then it diffusely reflects in all directions, it'll hit hit the reflectors a number of times. So after a given reflection from the faced reflectors, um, the observed intensity after the first bounce is L lambda S lambda times F lambda times C sub K lambda. So essentially the observed intensity before was times the spectrum of the reflector. So after the nth bounce, if this happens multiple times, each time you multiply it by F lambda, which is the spectrum of that filter. And so we have this formula here. And the range of bounces will be zero. Range of I will be 0 through n, which is the number of reflections. They call it bounces, so we'll continue to do that. Um, so in this model, each reflection within the system changes by F, like we saw in the previous one. And so, given that we know the spectral, or given that we know that the spectrum of the light source, spectral sensitivity of the camera, and spectrum of the colored filter, um, the problem is to estimate the spectral reflectance as lambda. Um, and so we would do that by solving the equation, which they've put into discrete form here, essentially to make it easier to optimize and actually calculate. So here, simply they just made it into discrete formulation of the integral that was there. Um, and then the constants here are knowns are in A, since that would equal a single value. And then lambda b to lambda e is the range, which is the wavelength that we're observing. So in matrix form, we can put it like proposal like this. And when we are observing all three channels, since RGB for the camera, after n bounces, then we can formulate the equation like this: y equals as. And again, so A is a combination of our knowns, which is the illumination, spectral sensitivity, and the color filter. So as you can see, um, we can we can pose it as an optimization problem in order to solve um, S, which is the reconstructed image. As you can see, based on this, the reliability of the result of the optimization is going to be based on the rank of A. Uh, so they pose a formula here, which is a way to evaluate the condition number of the result. That way we can know if the result of S is reliable or not. And the condition number of A can be defined as sigma max over sigma min, which is the maximum and minimum singular values. So these singular values represent the highest and lowest bounds of the matrix transformation on a vector. So given that we know, again, the illumination, camera sensitivity, and filter spectrum, we can use this to optimize the optimal color filter, which will give us the best result. Which you can see they have two parts in the experiments. One is based on simulation, and one is based on real data and actually capturing an image. So in the simulated part, they use this to pick the optimal filter for capturing. And so they additionally apply two constraints on the problem, which is the spectral reflectance constraint, which is just based on the fact that reflectance has to be within 0 to 1. Reflectance above 1 doesn't make sense. That's the natural bound of it. And then a smoothness constraint. So this is not necessarily a geometric constraint, but essentially they're saying that reflectance values seen in actual captures from hyperspectral cameras have a smoothness to it. They're not, jumping from one area to another without, a gap in between. And so they place a smoothness constraint, which will help their optimization. Um, and then, yeah, so D is the second derivative of the spectral reflectance, which we're trying to estimate. So this is essentially just to put in the smoothness constraint that it has to stay within a certain value that the spectral reflectance estimated is smooth. And so the previous equation is what we'll use to reconstruct the image. And we can write it in this form, which is simply just in the form that's optimal for programming it, which they solved using they implemented in Python and used CVX OPT, its optimization library, to perform solving this equation. Then this should be magnitude. So going into the implementation, they propose two techniques: the coupled mirror and kaleidoscope setup. They propose two, but in their actual experiments, they use the coupled mirror setup. So the coupled mirror setup is essentially what we see in this figure. These two lines at the bottom and the top are mirrors with the color filters attached to them. D is the distance between them, Z is the distance between the target, which will be here, and the camera. And then theta here is the angle of view of the camera. So based on this setup, they know that the number of bounces is limited to the floor of C over D times tan theta over 2. That is the geometric limit of the number of bounces. However, they state that n in their actual experiments is limited by the energy of irritants, which essentially is just to say, if we manipulate these values so that this number is very high, that doesn't necessarily translate that that many number of bounces could be possible, and essentially just because some energy is going to be lost in other areas with each bounce. And then also A in the equation must be vertically long or square in order to perform optimization. And then they also state that the spectral resolution of wavelength is limited to lambda is less than lambda over 3n. So this is also, putting a geometric bound on what is possible in real life when they actually do this. They also briefly talk about the kaleidoscope setup. Um, and the idea is similar, it's just that you would have more than, instead of having a mirror at the top and bottom, you would have, in this case, 4, which is a quadrangular pole kaleidoscope. And so the benefit here is that we can attach a different color filter to each of the sides, which, you saw from the equation, they'll be able to capture a broader spectrum because each reflection that will bounce off each side, will likely be different, and so then the observed spectrum by the camera will be more granular. And so the equation would change like so, and this is for if we have two different color reflectors, and if we had three, we would add another term, or four, another one. And so here I is 0 to NF, which is the number of bounces allowed for the F filter, and I to NG, which would be the number of bounces allowed for the G filter, allowing for n squared possible combinations. If the angle of view is horizontal. So obviously since there's multiple reflectors here, this would allow for more combinations than the coupled mirror setup, which only has 2. So going into the experiments that they ran, so they said that the wavelength that they observed was 400 to 700 nanometers, which is the visible light spectrum. So their data includes multiple sources, and they essentially take spectral reflectance curves from a number of different data sets, and then they perform a simulation based on these, and then perform the same simulation on real data, and then capture a leaf based on choosing the right reflector and then display that compared to a hyperspectral image. So here we can see they measured the reflectance of 253 color filters and the thin orange color filter with spectrometer. So this is needed for the equation. Um, so this is F lambda. And then they measured the spectral sensitivity of the camera used, Nikon D5100, based on some PCA methods proposed in another paper. And so this shows the curve, um, spectral curves for each of those, the color filters here, and then the sensitivity of each channel. So higher, if we look at RGB, higher will mean higher sensitivity at that area. And then for the filters, this is just essentially the ratio of light which will pass through at each uh, reflection. So for the synthetic data part, they simulated observations for each bounce on each channel of the camera for each of the filters and the clear orange filter. And then they repeated the same simulation for each of the samples based on the curves of their data set. And then I repeated again with some noise added to the data set. They solved the reconstruction based on the equation that they had before and evaluated the result of each with root mean square error um, to the ground truth. And so then here we'll see essentially this is where they plot the average RMSE for each filter compared to the ground truth in their data set. So as we can see, the average RMSE is 0.03 with an average reconstruction error of 2%. So it is actually fairly accurate. But we can also see that at shorter wavelengths, there's definitely larger discrepancies than at longer wavelengths, which you see towards the end of these graphs. And this is likely primarily due to the number of observations at that wavelength. So if the number of observations at that wavelength is less, the reconstruction is going to be more inaccurate. So this is with the light sky blue filter. We can see similar things. The average RMSE is slightly lower, 0.01. And then they report the condition numbers, so this is essentially the reliability of those results. These seem to be, you can see, on average more accurate than the orange color filter, but we can also see similar things on the lower end of wavelengths. So here they're showing essentially this is the optimization for choosing the optimal filter for the reflector. As you mentioned, given that we know we can choose the spectra of the filter and we know the spectral sensitivity of the camera and the illumination, uh, with those givens we can choose the optimal filter, which results in the lowest um, RMSE for the materials. So here we can see they chose the top six, and this is the lowest with 0.015. This is slightly higher with 0.045, and this is what they would use, or that they used for the real data um, and capturing the target. Um, and so they also plotted the RMSE for different samples in their data set. Here, these are the top 8 materials for the essentially worst reconstructed. And so what they observed from here is that when the spectrum is smooth, the RMSE is lower. When the spectrum has sharp changes, so this red one here, so over here, has a sharp change in the reflectance curve. The RMSE is higher, and this is primarily just because of that smoothness constraint that they put in their optimization. So here they plot the average error with the condition number. And so essentially this graph is just supporting what they guess would be the case, which is that higher condition numbers are going to have higher error because the result is not stable, is not reliable. And so based on this, again, they can choose the optimal color filter, which would be over here, which has the lowest condition number. And so then they, based on the optimal color filter that they chose, they tested with some real data. So in the real data setup, they used Nikon D5100 and D65 light source. And the length of the reflectors was 100 millimeters, intervening distance 20 millimeters, angle of view is 120 degrees. And they mentioned that up to 8 bounces can be observed, but in reality, only 4 were observed, again, due to the energy, physical interference between the camera and the setup. And so we can see for red, green, and blue, the reconstruction results roughly fit the ground truth for all color ships, with the error for green being 0.09, red 0.13, and yellow 0.20. And then in their last experiment, they tried to capture a leaf as a target in their setup. So due to the target being very small, in this case, only 2 bounces were observed. And just visually based on their 2 samples here, we can see that the reconstruction is not bad. So we can see at 550 nanometers we have roughly same reflectance. At lower, shorter, and longer wavelengths, the reconstruction is definitely higher. And again, this is based because of just the number of observations at those wavelengths. So looking at these up closer, so this is a real hyperspectral camera, and this is their one-shot approach. So we can definitely see roughly the same object. This line over here is just based on how, because the leaf was folded, so they had to capture a specific area of the leaf. They can only capture flat geometries and not complex geometries. So we can see that it's roughly similar in the range of 475 to 587 nanometers. And again, at the shorter and longer wavelengths, the error is definitely higher. So some discussion on those results. The main idea is that this approach is definitely feasible. It is possible to reconstruct the spectral reflectance in the image with the coupled mirror setup. And so they mentioned that based on synthetic data, they can choose. They know that the color filter is definitely impacting the result, and it is important to have the light source be stable. And they also observed that the number of bounces is definitely limited due to attenuation and light intensity and physical interference between the camera and the setup. So this is, the N is limited. There's a geometric constraint to it, which we saw in the previous slide, and then just in reality, they can only observe up to so many bounces, which impacts their reconstruction. And also that they noticed with the orange filter, although it's very thin, some amount of light is reflected in other directions. So we saw in the model of the cover filter that each reflection is supposed to go directly, in one direction, but some amount will go in other directions each time. So that results in a more unclear image after each bounce. Um, and again, so for their experiments, they were looking at 400 to 700 nanometers with visible light. Again, this is different from actual hyperspectral cameras, which capture the entire spectrum. And so, as you saw, the quality of reconstruction obviously is not identical to a commercial hyperspectral camera. But again, it is close to some degree, and it can still be used for many applications. And also considering the cost reduction, it might be optimal, or it might be chosen. Um, so more on some discussion of the limitations here. Um, so they cover some trade-offs between the spectral and spatial resolution. It suggests that essentially a higher spectral resolution requires n to be high, but if n is high, then the spatial resolution is small, and if n is larger, by shortening the intervening distance, it leads to a narrower field of view, and you essentially so you each either maximize your spectral resolution or your spatial resolution, but as you go in one direction, you're diminishing the other. They also observed that as the number of bounces increases off the reflectors, their signal to noise ratio decreases, and so this results in more unclear images. And then also, as they note for the leaf, which had a curve in it, the current uh, method that they propose is limited to flat geometries. Um, and so they mentioned that working on complex geometries is maybe a target of their future work. And it's difficult because it requires shape reconstruction um, to find um, the corresponding the corresponding points between the different bounces observed. Um, Ending off with the conclusion. So in conclusion, they propose a novel one-shot hyperspectral imaging technique, and they propose two different setups for this. They evaluated on the coupled mirror setup and show pretty good results. Average reconstruction error of 14%, significant cost reduction. So the main thing that this provides is it dramatically simplifies the imaging process. It makes it more accessible and significantly cheaper. And although the accuracy is still low compared to an actual hyperspectral image, the idea is that the problem formulation that we went through and sort of the constraints of it as well are correct, and it is feasible to capture a hyperspectral image with this setup. So it is possible to potentially improve on this and continue to improve those results. And so that's all we have here. And then if you have any questions, feel free to email me or however you want to reach out to me. Thank you.